Welcome back to the MOVI-C Control Cabinet Products Basic to Intermediate Training. This is session 16 and lab number 8. All right, we are definitely moving up to some more advanced topics now. We're going to be looking at something very interesting and important. We're going to look at another motor control mode built into MOVI-C products, CFC, also known as current flux control. We're going to look at how to start up a motor in CFC mode, and we're also going to look at how to measure and tweak the load inertia for the best possible motor performance. Let's get started. First of all, motors. What do you need to use for this lab? You can use either motor type as long as it has an encoder or resolver. You must have feedback in CFC mode, but you can work with asynchronous or synchronous motors, no problem. I'm going to be using a servo motor for my lab. The instructions for asynchronous are practically identical, so you should be able to use just one set of instructions for either motor type. We have some fairly hefty pre-lab instructions. I need to give you a lot of background to really understand what we're doing in this lab, so this lab will be a little longer. Perhaps you even want to split it up by watching the pre-lab and then stopping, taking a break, and then coming in and doing the walkthrough. Your call. Whatever you like to do, let's get going. Something very important to understand, all applications have realities. Now, what do I mean by that? Well, the conditions that influence how the application behaves under VFD motor control. What we're going to be looking at specifically here is the fact that the load has mass. It has mass, or what we commonly think of as weight. And because it has mass, it has something called inertia. And if you've taken physics, you know what inertia is. In fact, you know that inertia and mass are practically considered the same thing because they directly correlate to each other. Inertia is resistance to change. In other words, a given mass, if it's not moving, does not want to move, and it will oppose having to move. And if it is moving, it will oppose having to stop moving. Resistance to change, in other words. And I've shown you a really good example of a very massive load. It's a roll of sheet metal that's being rolled up. That has enormous mass. Therefore, once it is turning, it does not want to stop turning. And when it's stopped, getting it turning is a lot of work because it has a lot of inertia. So we need to take into account the load's inertia when we control it with a VFD. And if the VFD is not set up correctly, it may have a great amount of difficulty controlling that load. Now, application needs vary depending what the application is, and the amount of accuracy we expect from our drive control is going to vary as well. Let me give you two extreme examples, a loose one and a precise one. All right, the first one is a gravel conveyor. We're just moving gravel at a given speed down this conveyor. When we start or stop it, I don't think we care if we stop 6 inches further down than we expect. After all, it's just a gravel conveyor. But on the other hand, our second application, which is some kind of factory positioning system that moves what looks like auto body parts to specific places, well, that's a very precise application. It's got to start and stop with millimeter precision. Otherwise, you could get into some problems. Now, as you can guess, you need to take mass and inertia into account when dealing with precision. If you're going to move something with precision, you have to be able to deal with the effects of inertia. And that is what brings us to talking about how the VFD decides what to do. It uses its built-in control system, which is actually a program running inside the VFD, and that is taking into account things like inertia and what you're requesting of the application. The control system is taking into account all these factors as it's trying to control the mass out there and give the precision you want. So we're going to transition to talking about control systems and how they work. And this is just a very simplified explanation of control systems. You can take whole college courses on control systems, and I'm going to explain them in about 5 minutes. So this is very basic. Ultimately, every control system, no matter what it is, whether it's the thermostat in your house controlling the temperature, the cruise control on your car maintaining your speed, or a VFD trying to position something with millimeter precision, the ultimate goal is maintaining control. So the control system, whatever it is, must handle any change of load, set point, or direction, and it must control the system in a way that everything goes as well as possible. Let me show you a simple illustration. All control systems kind of look like this if you graph them. You have a graph where the x-axis is time and the y-axis is graphing what's called the process variable. Maybe it's the speed the motor's running, maybe it's position, maybe it's torque. It really doesn't matter. The process variable is the red line. It's showing what's actually happening to what it is you're controlling. Now, the blue line represents the ideal condition, what the system wants to happen. Maybe the set point you've set, or maybe a change in the system that the system has to accommodate. Let's just assume, for example, at the moment, the blue line represents a change of set point, changing from one speed to a higher speed. What's going to happen is you're going along, the system is running smoothly, the red line is relatively flat, the speed is running at one speed, and then all of a sudden you initiate a change. You say, go to a faster speed. Now, that set point change happened instantaneously, but the real-world application cannot change instantaneously because remember, it's got mass and inertia. It can't respond instantaneously, and of course a motor can't respond instantaneously either. It's got mass and inertia. So you notice the red line doesn't change immediately to reflect the blue line. There's a delay. And then when the change comes, we see some adjustments happening, but often problems like overshooting and undershooting the new target, and eventually settling to a new level. All right, this is always going to happen in every control system. The quality of the control system will influence how fast it will settle to the new level and how much messing around it does as it's overshooting and undershooting before it settles. Really good control systems can bring you to the new set point very quickly. Poorer control systems will take longer. Let me give you one other example of a change rather than a set point change. Let's say a load change. Maybe you have a conveyor belt that's running at a fixed speed and it's empty, and suddenly you throw a box on it that weighs 500 pounds. That's a change, and it happened instantaneously. The VFD has got to compensate for the increased load to keep the speed running, and it's not going to do it instantly. It's going to take some time, and the control system is one of the factors that determines how smoothly and quickly it makes that change. Of course, also the motor has to be properly sized and so forth as well, but we're mostly concerned about control at this point. There are many different ways to implement this in software, but the most popular one, and the one that is in MOVI-C VFDs, is something called Proportional Integral Derivative, or PID, control. PID is an algorithm that involves some very sophisticated mathematics, and it does really good control. So we're going to just do a quick summary of how PID works. Let me show you what a typical control system looks like. We have a set point, SP. That's what we want it to do, the value we set into the system, like 2000 RPM. We also have the process variable, which is being controlled. In our case, it's usually a motor. And that outputs a value which we call the process variable, maybe how fast the motor is turning. And we can measure that with feedback devices like encoders. Now, if we have that feedback, we can feed it back into the control system and provide that information so it can judge how well it's doing. What the control system does is it takes the set point and subtracts the process variable from it. And that gives us a number, which is usually not zero, which we call error. And that indicates how far off the mark we are. The control system's goal is to reduce error as close to zero as possible. You probably won't get it exactly at zero, but you want it very small. Because if it's very small, it means the control system is doing a really good job at achieving the set point. All right, so how does it do that? Well, it feeds the error into the software algorithm that makes corrections. We'll just call this control. It's this green diamond-shaped box. And the control system does some math, and it comes up with a correction, which we call a control variable, and it feeds it back into the process and tweaks it to try to alter it to improve the situation by reducing the error. And this just goes on constantly as the system runs. It keeps measuring the feedback, calculating the error, tweaking the control variable, and trying to bring the process to the point where the error is really low. And this just happens over and over and over. So now let's zoom in on the control algorithm, the green diamond-shaped box, and look at what's going on inside. In a PID system, there are three equations being calculated inside the green diamond. It takes the error, it takes set point, subtracts process variable, feeds that into P, I, and D, and those three equations do their math, the result is added together, and then that gives the control variable. So what is P, I, and D? What does proportional integral derivative mean, and why do we need three equations to achieve it? Okay, short answer is this. The proportional equation calculates the present condition. It figures out about how big the error is. That's why we call it proportional. It's looking for the size of the error. The idea is if the error is really big, we need to do a really big correction. If it's really small, we do a small correction. So it's just looking at what is the situation like right now. It's estimating the size of the error and making a correction appropriate to it. Integral looks at the past. Integration, if you've taken calculus, involves examining the accumulation of something over time. So what it's doing is it's been keeping track of how the system has been behaving in the past, and it's estimating the quantity of error. Has the system been doing a good job or a bad job in the past controlling things? If it's been doing a bad job and there's a lot of historic error, it's going to do a bigger correction. If the historic error is fairly small, it'll do a smaller correction. So that's what integral is for. It's looking at kind of the history. And then derivative, as you can guess, is looking at the future. It's looking at the rate of change. And again, if you've taken calculus, you recognize the term derivative. It's kind of a measurement of the rate of change. In other words, it's sort of predicting the future. It's saying how fast is the system changing. If it's changing really fast, then we probably need a bigger correction. If it's not changing very likely in the future too much, then a smaller correction is fine. So PID works so well because it's looking at the present, the past, and the future. And based on that, it's creating a composite correction that is creating the CV that tweaks the process and hopefully improves the process variable, which lowers the error. So there's PID control in a nutshell. Hope you found that fun, and guess what? Hardly any math at all. All right, so the MOVI-C VFD has different motor control modes. It actually has 4, as you know, VF, VFC+, CFC, and ELSM. Let's look at how good they behave. VF and ELSM mode are both open loop modes. So as you can guess, they give the poorest control. They're fairly sloppy compared to the others. They take longer to accommodate change, and they do a little more overshooting and undershooting, but they get there in the end. And ELSM is actually pretty good for an open loop mode. VFC Plus is either open or closed loop. Of course, it behaves better when it's closed loop, but even open loop, it does a really good job. Definitely better than VF mode. As you can see, it corrects faster and it does less overshooting and undershooting before it settles. CFC mode is really good. It's a closed loop mode only. It must have a feedback device, but it gives really tight control. And you can see it corrects quickly. It barely overshoots and undershoots, and it just locks on. So that's the mode that we really recommend you use with SEW motors with feedback. So if you have one of our motors and it has a feedback device on it, most of our field engineers recommend using CFC mode unless there's a compelling reason not to. We have digital motor models in the VFD. It knows our motors really well, and it can give you really super control in CFC mode. Now, if you're using a third-party motor, you're probably going to use one of the other modes. But if you're using one of ours, I recommend CFC. And that brings us to a very important term and one associated with this lab, and that is tuning. What is tuning? It is adjusting the PID loop to control the load quickly and accurately, handling changes smoothly and safely. You can tweak those PID factors in order to adjust the control system, and that process is called tuning. Now, there are 2 ways to do it. The first is a really easy method. It's the one I'm going to show you in this lab, and it's practically automated. The other is expert only. I'm not going to show you that because this is not an advanced class. You actually get into some parameters and you start twiddling the P and the I values and making some adjustments to them. You really need to know what you're doing, though, to do that. What I'm going to show you, you don't. The built-in tools help you a lot. So in order to do the easy kind of tuning, which is what we're going to do, you have to set 2 factors, the load's inertia and how stiff you want the control system. Stiff is how responsive, how precise it's trying to be. The stiffer it is, the more responsive it is to change, and the more aggressive it is about correcting problems. Now, how do you get the load inertia? Well, you might know it. With some applications, there's engineering information that's available, and you can just key it in actual inertia units. But what if that's not the case, which is true for many applications? MOVI-C can measure it, and that's what we're going to be doing in this lab. Now, we won't get a very impressive measurement because we're using a motor with just a small flywheel on it, so we don't have a big load, but I should still be able to demonstrate it. Now, the motor you have may be too lightly loaded to really measure it very well, but in the real world, this technique is great. So you don't have to know it, you can measure it, you can pick your stiffness, and then the system will adjust the PID loop just perfectly to control things and make things work really well. Okay, enough said, let's get in there and do some CFC work. So pause the video and do the lab. Okay, well, I hope you found that fun and interesting and thought it was pretty neat to see how the automatic inertia measurement worked. Let's go ahead and do our lab walkthrough, so if you had any problems, we can clear them up. And if you didn't have an appropriate motor, you can see how this works. Okay, well, let's explore CFC mode. As you can see, I'm still in ELSM mode with that velocity drive MOVI kit installed, so this is right where I was on my last lab. I need to make a few changes here in order to run in CFC mode. First of all, of course, I have to reconnect my encoder cable because CFC mode requires an encoder. Now, I've already done this, and I've done it with my drive turned off. You should never connect an encoder cable with the drive powered. That can damage either the encoder interface or the encoder itself, so do that powered down. Now, once I've done that, my servo motor is fully functional and capable again with feedback. My particular motor has an electronic nameplate, so I should be able to use that when I do the startup. Yours may or may not. Of course, if it doesn't have an electronic nameplate, you'll need to enter in the nomenclature off the physical nameplate, but I'm going to show you an electronic nameplate. So let's dive in and go ahead and get reconfigured in CFC mode and then play with the inertia. I'm going to click the top part of the axis circle first of all, because that takes me to the device properties menu group. I'm going to pick basic settings and I'm going to do a delivery state. I want to have a clean VFD to do this, so I'm going to go ahead and restore the delivery state. You've seen this a number of times now, nothing new here. And that's completed. We've factory reset our device. Okay, so now we're ready to go ahead and commission the drive. We'll go to drivetrain 1. And you notice it has found the electronic nameplate and it's shown me what it contains. Now you should always double check that that information is correct. If someone has changed the encoder on the drive and swapped it with one from another drive, the electronic nameplate could be wrong. That can happen when maintenance people aren't careful about those things. So you should check it. Now I've looked at this here and I can see that my voltage, my speed class, brake and temperature sensor, as well as encoder type are all correct. I've confirmed those with the physical nameplate. So I'm going to just go ahead and click Use Electronic Nameplate. If it was wrong, I could always click Read Motor Nameplate and then I could key in the nomenclature manually. But I'm going to accept my electronic nameplate and be grateful for its assistance. I'm just going to double check everything screen by screen to make sure there's nothing weird. Everything looks okay on this screen. All the connections are correct and all the devices are correct, so I will continue to the next screen. I will accept this encoder details screen. Everything is fine here. And the last thing I want to do here is go ahead and set pulse width modulation to 16 kilohertz for some peace and quiet. Of course, notice it's selected CFC mode and it's not giving me any other choices because when you have an encoder, that's really the only appropriate choice. I do need to set my line voltage here. I'll set it to 460 instead of 400, the European standard, and I will click Continue and Transfer Drivetrain. So this commissions my motor and we're all set. So that takes care of it. We're now commissioned in CFC mode and ready to take full advantage of what this servo can do. Now, before we can do any optimization or inertia measuring, we do need to set some limits. So I'm going to go to the monitoring functions menu and pick limit values, and I'm going to set the maximum positive speed to 4,500 RPM, which is the motor's maximum speed, and I'll set the negative speed to the same. I'm going to set acceleration to a value 4 times that, 18,000, and I'm going to set the deceleration to that as well. By setting it to 4 times 4,500 RPM, that means if I go from 0 to 4,500 RPM, I will have a 1/4 second ramp, which for this application is acceptable. All I have is a flywheel on my motor, so I don't really have a big load. Of course, you would set that to whatever's appropriate to your application. So this is good for demoing when you have an essentially unloaded motor. All right, we are now ready to measure the inertia and optimize the drive. So we go to a new menu we haven't visited before, and that is Optimization DT1. And it has 2 submenus, Set Load Moment of Inertia and Set Controller Dynamics. The first thing I'm going to do is set the load moment of inertia. So I pick this submenu and I click the button Determine Load Moment of Inertia. Now, if I know my actual inertia, I could pop this menu down here and make a selection either from some number of times the motor's inertia, or I could just key a value in. In this case, I don't know what the inertia of my motor's flywheel is, so I'm going to measure it by clicking the Determine Load Moment of Inertia button. And it asks me to go into manual mode because there is a manual mode setting that facilitates this. So I'm going to click Open Manual Mode, first of all, and I'm going to activate it. And I have to remove controller inhibit so my drive can run. And you notice it's in a new mode we haven't seen before called Load Cycling Distance Absolute. What it's going to do, it's going to zip the drive back and forth, kind of like a shoe shine mode where it goes left and then right, left, right, as fast as it can. And it's going to measure the jerk as it changes direction. And based on that, it'll be able to estimate the inertia. So this is a mode that makes inertia measurement really easy. Now I have to do a few things to set it up, so we need to configure this correctly, but it's pretty simple. The first thing I have to do is reference the drive. Now we're going to talk about referencing in a lot more detail down the road. Right now we're just going to use a quick and dirty referencing mode that says where you are at the moment is 0. So I'm going to click the little gear symbol to pop up some extra settings here, and I'm going to click this button, Start Reference Travel. And my drive clicked and said now it's at 0. So that was kind of like the really easy referencing mode. I'm going to set my acceleration slider all the way to the top. When you measure inertia, it's usually best to do really quick ramps. Now, of course, you always have to be compatible with whatever your application is. You don't want to break something. In my case, since it's just a flywheel, I can be pretty rough. But again, this is application dependent. The general rule of thumb is pick the fastest ramp that you can safely use. We also want to do this at the highest speed we can support. I'm going to just key in 4,500 RPM. Again, this is application dependent. And finally, I'm going to enter 100 into the position 2 box. So it's going to cycle between 0, where I currently am, and it's going to turn 100 in revolutions, and then it's going to reverse. So that is the setup. I'm all set to go now. I'm going to press the play button, and the drive will start cycling. And it is whipping back and forth right now. And you notice it's automatically taking measurements. And it's just going to do this forever until I stop it. How do I know when it's got what it needs? Simple, when this button turns green. It turned green after, I think, just 3 bars. So it has now gotten the inertia, so I can just click End Measurement and save value, and then I can stop manual mode. And you notice there's my inertia value right now, 1.658 kilograms square centimeters. That is an inertia unit, if you didn't know that. All right, so we have successfully measured the inertia. It's not very big because it's not loaded to anything, but that is it. And that has helped tweak the PID loop to optimally control this particular drive. All right, so that is done. Now we need to set the stiffness. That is how aggressively we want the controller to attempt to maintain the set point. So I go to the second menu, Set Controller Dynamics, and I have a slider here that goes between 0.5, which is very loose, sloppy stiffness, to number 2, which is extremely stiff. What can happen, of course, if you're too soft, the drive will be very smushy in its performance and it will not be very accurate. If it's too hard, it will start to oscillate and probably fault. 1 is in the middle here, even though it's not in the middle of the slider range. That's considered kind of a good starting point. I'm going to just leave it set at 1 for now, but of course you would definitely have to tweak this with a real application. I'm going to do one other thing here. I'm going to set the zero clearance slider to 0 backlash because I don't have a gearbox or anything connected to my drive. All right, that is all I have to do. My drive is now pretty optimal. The PID loop has been tuned for fairly normal behavior, reasonably stiff control behavior, and it has the proper inertia. So that is pretty much it. Now let's just do a little testing. We're going to play with some other features that manual mode has. We're still in manual mode and I haven't deactivated it. We've been using load cycling. Let's look at something else here. We have position controlled manual mode. There's our old familiar speed control, but here's position. I'm going to pick this, and this allows me to send the drive to a position at a given speed. Now it's already referenced, and here's my actual position. I'm at 83.08 revolutions. That just happens to be where it was when I stopped the drive. So let me go ahead and send it somewhere. And I'm going to pick a positioning speed. Let's do it at 1,000 RPM. And I'm going to set my acceleration to something maybe a little less aggressive. Maybe I'll set it to 4,000 RPM per second. All right, and I'm going to go up to a speed of 1,000 RPM. All right, so first let's just go to 0. I'll click play, and my drive is going at 1,000 RPM counterclockwise. Notice the position there, and it's just arrived at 0. All right, let me give it a new position. Let's say I want to go to minus 150.2 revolutions. Off it goes. So you see, you can test positioning with manual mode as well as speed. Manual mode is a very versatile tool. And there we go. You can see it arrived at negative 150.19. Pretty good. All right, and that is really all we had to do. So this was actually, all things considered, a relatively simple lab, but you can see how we were able to measure our inertia very easily, tune the control system without being an expert in PID adjustment, and take full advantage of manual mode to almost automate the process. So we are pretty much done. Let me deactivate manual mode, and before I say yes, I'm going to turn controller inhibit off just to be safe. And I'm going to click yes, deactivate manual mode, and I'm going to close it up and go back to my access circle, and there we go. That's it. And that is the end of session 16. Good job. We're definitely chomping through our labs. In our next lab, we're going to move on to using a really nifty tool that is part of MOVI Suite called the scope. The scope lets us do some very powerful things. It's a very important tool, but it definitely takes some explanation to understand it. So we're going in for another big lab, so get some coffee and see you next time.